In this unit, we'll discuss and do some examples for 5 different properties which are related to circles. Now, the properties themselves are further explored in university in courses that are related to Euclidean geometry, though the general skills are used in grades 10 to 12. Now, while we learn about the properties, we'll also learn a few definitions just to help understand what those properties actually mean. So one definition is talking about what a tangent is. So tangent is a line that intersects the circle at exactly one point. So if you have any kind of, well, let's actually make that look like it's actually intersecting. So it's basically going to touch at one point. So the first property that we're going to talk about is the tangent radius property. So the tangent to a circle is perpendicular to the radius at the point of tangency. So what that means is if you have any kind of line, no matter where it is, and it touches the circle at exactly one point, wherever you, yeah, actually make that look like it's actually somewhat going straight. If you draw something that goes through the radius, it's going to create a right angle. Perpendicular means right angle. So 90 degrees. So in the specific example here, it says angle APO, so APO, so that angle, I'll make it actually colorful, is actually also equal to angle BPO, so BPO, which equals 90 degrees. That's the first property. It's pretty nice and simple to start understanding. So we're going to deal with an example that relates to that. Point O is the center of a circle. So this point right here is the very center of the circle. AB is tangent to the circle. So it means it's touching in exactly one spot. In triangle AOB, notated usually like this. Usually you draw a triangle and you say AOB. Angle AOB is 63 degrees. So if you're talking angle AOB means you start at A, go to O, then you go to B, and the angle that's contained in there is that one. It's saying that's 63 degrees. What we need to do is we need to determine what is the angle or what is the measure of angle OBA. So OBA is asking, well, what is that? And this is the idea of a property that we will be using in further years. Tying back to our first property, the tangent to a circle is perpendicular or 90 degrees to the radius at the point of tangency, meaning this tangent line AB is creating a 90-degree angle with the radius OA. So one property that we're going to be using in further years is how many degrees are in a triangle. I believe that you would have done that property back in grade 6, so it's been a little bit of time since you've actually worked with it. But it's not going to be the end of the world to remember that a triangle adds up to be 180 degrees. So meaning if all these angles add up to 180, this one's 63, this one's 90, to find out what this angle is, we just have to take 180, subtract the 63, and subtract the 90. It gives us 27. So this angle right here, so angle OBA is 27 degrees. Not bad for a start. Now let's get into a more complex one. An airplane A is cruising at an altitude of 9,000 meters. A cross-section of the Earth is a circle with radius. Now I do specifically know that the Earth isn't a circle. It is a more of a sphere, which means it's a little more oval-like. But we are just learning the properties so we can apply them. So the cross-section of the Earth is a circle with a radius of approximately 6,400 kilometers. Passenger wonders how far she is from point H on the horizon that she sees outside the window. Calculate the distance to the nearest tenth of a kilometer. So this is going to be our center of the circle. Centers of circles are usually notated with an O. Now let's identify a few things. So here's an airplane. It's flying out. Person's here and asking, well, how far am I from this point? Same time saying that's cruising at an altitude of 9,000 meters, which means above the Earth, it's 9,000 meters. The Earth is approximately, I know it's an oval, but it's approximately a circle with a radius of 6,400 kilometers. One thing to note is 9,000 meters is actually 9 kilometers. So the beautiful thing is that no matter your circle, your radius, whether it's there, they're all going to be the same length, all going to be 6,400 kilometers, which means that is 6,400 kilometers. And because of that, because this line, does it actually say? Yeah, if you're cruising out here and you see here, well, it's only going to be touching this point in one spot, which means that this is a 90-degree angle. So now that we have this triangle, now I'll just draw it again. This side is 6,400 kilometers. And in total, this side, I know that's not drawn proportionately. This side is 6,409 kilometers. We have to find out what is this. Well, it's a great thing that we had learned a special property or special theorem starting from grade 8. Our Pythagorean theorem. A squared adding our b squared equals our c squared. So first off, this is our c. These two sides could be interchangeable. One could be a, one could be b, and it doesn't really matter. We'll call this one b. So that means that this is a. So we have a squared, which we don't know, so it's x squared. It's going to be adding our b squared. Well, we know what b is. It's this 6,400. And it equals c squared, which is 6,409 kilometers squared. When we're solving equations, ideally we simplify our sides first, which means 6,400 squared, 4096,000 equals, and 6,409 squared is let's see, what does it work out? 41,075,000 281. So to manipulate, to get our x squared by itself, we subtract the 40,960,000 from both sides. So x squared would equal, so 41,000 subtract, so the 41 million subtracting the 40 million number is 115,281. Then to get our x by itself, we take the square root of both sides. X would then equal, so it says calculate the distance to the nearest tenth. It works out as 339.5 kilometers. So if someone is cruising at an altitude of 9 kilometers above the Earth, and they're just looking out towards as far as they can see, they're approximately 339.5 kilometers away from it. Alrighty, next example. Well, actually, we start off with a definition. So a definition of a chord. So a chord is a line segment that joins 2 points on a circle. So any kind of line that joins 2 sides of a circle is known as a chord. So this is a chord. I can draw a chord that goes like that. Again, that's a chord. So you may be asking, well, what about the most special chord? Of course, probably the most well-known chord is the one that goes straight through the center of the circle. And the chord that goes straight through the center of the circle is the diameter. So the diameter is just a special chord. But all chords just connect 2 sides of a circle. Which brings us into the second property. It is known as the perpendicular to chord property. Now it has 3 parts of it, which really, they tie so well into each other. They are known as, well, the first 2 for sure are known as biconditional, which means if you read it one way, it also reads the other way. So here's the thing. A line drawn from the center of a circle to a chord bisects the chord. So first off, I didn't want to put an extra definition in because bisect is such a small definition. But bisect just means it cuts it in half. So meaning, if you have a chord, and if you draw a line from the center of a circle to a chord, so our center of our circle is right there, and if you draw a line to a chord, I see what I missed. I missed a word in here. The perpendicular line drawn from the center of the circle to a chord bisects the chord. So that means that if you were to draw a line that does go perfectly perpendicular, meaning makes a 90-degree angle with the chord, it's going to bisect the chord, which means this side of the chord is going to be the exact same length as this side of the chord. The second part of this real property is the perpendicular bisector of a chord passes through the center of the circle. So it really reads both ways. So if you draw a line perpendicular to it, it cuts in half. If you have a line cut in half, the line that goes perpendicular to it goes through the center. So it's read both ways, which makes it what's known as biconditional. You read it one way, well, you can read it exactly backwards. It's true both ways. And the last kind of part of the property is a line that joins the center of the circle and the midpoint of the chord is perpendicular to the chord. It's personally, I find it a little bit redundant to say it. Basically, if you extend this line straight out, we'll call this point C, it's still going to be perpendicular to here. So as long as you have a line that goes through the center, it's going to be perpendicular to the chord if you cut, and it's going to cut in half. So if you don't draw it 90 degrees to it, it's not going to be cutting in half, which means it's not going to be going through the center. So all those properties are just so interwoven together. Again, these properties really do come into effect in Euclidean geometry. Very few people are going to have to take that kind of course in university. No, I did, but that's because I'm a math guy. So let's do some examples. Oh, I haven't labeled them, sorry. Point O is the center of a circle. The line segment OC bisects chord AB. So OC is going to bisect AB. So what that means is this side is going to be the exact same as that side. So from AC, it's going to be the exact same as BC. It says that angle OAC, so this angle right here, is 33 degrees. We're going to determine the measures of X and Y. So here's a few special properties. Well, O is the center of the circle. Well, if O is the center of the circle, any line that is drawn from the center of the circle to the outside of the circle is the radius. And if it's the radius, that means those two sides are also going to be the same, no matter what measure it is. It could be 10 centimeters, it could be 5,000 kilometers. So here's the special thing. If OC bisects AB, it means that this is making a 90-degree angle. So we have two special properties here. You don't have to ever solve a triangle in alphabetical order. Sometimes it works, sometimes it doesn't. The first thing I can see right here, with drawing that 90-degree angle, I've now created a right angle triangle, which means I know how many degrees are in a triangle. It's 180. And if I subtract the 90-degree angle, and I subtract the 33-degree angle, angle Y would be 57 degrees. So we've solved for angle Y. Now we just have to solve for angle X. Well, the beautiful thing about angle X is it's contained between this red side, this radius side, and the bisected chord, the green side. Well, this angle is also contained between the radius and the bisected side. This entire triangle is what's known as an isosceles triangle. And a special property about isosceles triangles is that the angles at the very bottoms of two sides that are the same are going to be equal, which means angle X is going to be 33 degrees. And that's all there is to it. Next example. A horizontal pipe has a circular cross-section with center O. Its diameter is 40 centimeters. So diameter going through the center, that entire side, or that entire special chord is 40 centimeters. Now water is slowly filling the pipe. So all of this is water. It says the surface of the water is 24 centimeters wide. So from here all the way to there is 24 centimeters. We need to determine the maximum depth of the water. Oh, I also don't have this fully labeled. Oh yeah, the C is there. It's asking basically, how deep is this water in this pipe? What is that? Well, here's a few special things. If our diameter is 40, our diameter can be written as 40 no matter where we go, as long as we go from a side and go through the center of the circle. So there's 40, there's 40, which also means if we're going through the center of the circle, we have the radius, which is 20 centimeters. Now at the same time, this entire side here is also 20 centimeters. So if we've drawn this line properly, we have made a 90-degree angle here. So this entire side is 20. We know really two things in here. We have a right angle triangle. Sorry, we actually know more than two things. One of them is we have a right angle triangle. This hypotenuse is 20 centimeters. And if we have this chord, and we have this line drawn perfectly to 90-degree angle, well, this entire chord has been bisected, which means instead of 24 centimeters, it's 12 centimeters. Now, of course, we know that from the center all the way down to the edge of the pipe is 20 centimeters. But we don't know what this part is. So we know that this entire thing is 20 centimeters. And if we subtract off this side, we will be left with what that part of it is. So we're going to have to use Pythagorean theorem again. A squared plus b squared equals our c squared. Our c is the 20. And it doesn't matter what I say is a or b. We'll say this one's b. And let's keep on going. So the b 12 squared is 144. 20 squared is 400. So to manipulate, I'd have to subtract the 144 from both sides. And 400 subtract 144. Got it wrong. Is 256. So we get the x by itself, we square root, and x So just that part of the triangle should be 16. Yes. So if this part is 16, we need to find out what is the depth from here to here. That's a nice quick calculation. We know the entire length is 20. We subtract 16, and we get 4. So the depth of this water is 4 centimeters. Now let's go into the the last kind of examples. So we have a few definitions. So the first thing is an arc is a section of the circumference of a circle. So the circumference is the measurement all the way around a circle. So an arc will be just a section of it. So we could say all the way from here, all the way around. Oh, hope you. I apologize for the crooked line, but this is an arc. It's a section of the circumference. Same time, I could draw an arc that just goes around here. I could have these points anywhere on the circle. It would just be an arc. Some special notes about these, though. If we go longer than halfway around, it's known as a major arc. This one, which goes less than halfway around, is known as the minor arc. A few more definitions in here. A central angle is the angle formed by joining the endpoints of an arc to the center of the circle. So if we have a center of a circle, a central angle is made by joining the endpoints of an arc. So, sorry, I don't want the arrow one. I just want the line. The endpoints of an arc to a circle, to the center. This angle right there is known as the central angle. An inscribed angle does almost the same kind of thing. It joins it anywhere else on the circle. So this angle right here is known as an inscribed angle. And the last definition here, right? Yeah, then we get the properties. Subtended means lines drawn from the ends. Lines drawn from its ends form an angle where they meet. So subtended is a little more of an ambiguous understanding. The inscribed angle and the central angle are both subtended by the arc AB. Just meaning we can create an angle here and an angle here by connecting these 2 points somewhere. So we've created it at the center and on a point at the end of the circle. Basically, we just created some angles here. These 2 angles are called subtended angles. All right. So third property. Last 3 properties go very quickly. It's the central angle and inscribed angle property. So what that means is if we have a central angle and an inscribed angle, so no matter where I've drawn it, my central angle and so I could draw it anywhere. I can move it way over here too. I'll make it over here just to make a point. And then this is my inscribed. The property states that the measure of the central angle subtended by an arc, so basically if you connect them at the same points, so at the same points, the central angle is always going to be twice the measure of an inscribed angle subtended by the same arc. So I will call, let's call this point C. So what that's saying is angle AOB is actually 2 times the size of angle ACB. So this angle right here is literally double the size of this one. You could also say it the opposite way. We could say that if you cut angle AOB in half, it would be the exact same thing as angle ACB. So again, if we cut this angle in half, it'll be actually the same angle as here. And that's just how it's always going to be. It doesn't matter where this point, this inscribed angle is. It could be here, it could be over here, it could be right there. It'll always be half the size of this central angle. Fourth property is the inscribed angles property. Now it states that all inscribed angles subtended by the same arc are congruent. So here's what that means. No matter what kind of arc you're using, so it works really nicely with that last property. Talking about the central angle, it means that inscribed angle, so that angle, no matter where you draw it, is going to be the exact same. All of those angle measures are exactly the same. I'm just going to make this actually connect properly. Well, I tried. And the last property, and then we'll get some examples, are angles in a semicircle property. All inscribed angles subtended by a semicircle are right angles. So meaning, if you have a semicircle, so half a circle, no matter where you draw your inscribed angles, so an inscribed angle can be there, can be there, can be there. Oh, sorry. Can be way over here. All of these inscribed angles, so the ones that are made right at the ends of the circles, those are all 90-degree angles. That's all it is. Now, obviously, you can tell that if you're talking about this shape here, well, this angle is not 90 degrees, this angle is not 90 degrees. That's because those are not the inscribed angles. The inscribed angle starts with those points on the circle and goes out to some other point in the circle. If we had another point, another 2 points, and we subtended them, or not, inscribed them with point B and point A, then we'd have a 90-degree angle. So what I mean by that, let's see, let's get a circle in here. So if you have a semicircle, so we'll call this A and B, we'll call this C and D. So if I subtend the arc AB with C, the reason that doesn't look like it because it didn't actually go perfectly there. This would be making a 90-degree angle there. At the same time, if you subtend C, not sub, sorry, inscribe CD with point B, so you draw the point again. It's not lined up. It's just not lined up perfectly. That's why it doesn't look it. Same time, you have to make sure the points are lined up exactly across from each other to be a semicircle. That might be actually the semicircle. That point will be making a 90-degree angle there. The last one is, well, last two ones, if you have AB and you connect them to point D, well, that's also going to be making a 90-degree angle at D. If you have CD and you're connecting them to point A, well, that's also going to be a 90-degree angle, which makes a nice rectangle. Of course, you can make a perfect square too, but you'd have to have nice perfect spacing. Just any kind of thing. So the three properties, talking about inscribed and central circles. So the central circle is twice the size of the inscribed circle. All inscribed circles or angles, inscribed angles are the same, and inscribed angles from a semicircle are always going to make a 90-degree angle. Sorry, just one more special thing. We'll talk about the semicircle. So we just said that all inscribed angles are going to be a 90-degree angle from a semicircle. Well, if we go back to this property, the inscribed angle is going to have to be half of the central angle. Well, if your central angle, if you have a perfect semicircle, your line is going to be going straight through the center. And if you're going straight through the center, that means that you have 180 degrees. So a 90-degree angle is exactly half of your 180. Sorry, math does actually excite me. It's fun to do math. Alrighty, couple examples here. So point O is the center of the circle. We're going to determine measures X and Y. So we have all of these angles are starting from the point, from the arc AB. So here's a few special things. Again, if we go back to property 4, all inscribed angles subtended by the same arc are congruent, or they're the same, which means we have this angle, which is inscribed with arc AB. This angle is also inscribed with arc AB. So X is 55 degrees. We go back to property 3. All inscribed angles are half the size, or half the size of the central angle. So if you double whatever this is, you get what your central angle is. So if we know that our angle here and our angle here are 55, this angle is going to have to be twice the size. So 110. And done. rectangle ABCD has its vertices on a circle with radius of 8.5. So the radius, so going from the center anywhere to the outside, is 8.5 centimeters. The width of the rectangle is 10 centimeters. So there's our 10.0 centimeters. What we need to do is we need to determine the length to the nearest tenth. So we need to determine what is that. Well, let's deal with the fact that I can draw a line perfectly down there. And if I draw it at a 90-degree angle, I now have a right angle triangle that looks like this. The center of the circle means that this side is 5.0 centimeters. So what we need to do is we need to find out what this is. So by our Pythagorean theorem, let's see, our A we'll say is X, the B is the 5, and our C is 8.5. So 5 squared is nice and easy to do. It's 25. 8.5 squared is 72.25. So I'm going to have to subtract the 25. So x squared, if I subtract that 25 off, I get 47.25. And take the square root. X would be 6 point, well, I'll put 87, but that's, sorry, that X is improperly labeled. That'd be that side. We need to find out what the entire, sorry, we have to find out what the entire side is. What we just found out is we only found out what is that part. So obviously, multiply by 2. And rounded will be 13.7 centimeters. But of course, this is math. There's not just one way of doing it. Because I could take this and extend it all the way across. Because I know that if we go through, if we have any kind of angle that is inscribed on a circle that goes through the center, so that half circle, we're going to make a 90-degree angle there, which means we could also have a right angle triangle that looks like this. 8.5 is only the radius, so double of that will be 17 centimeters. And then we can find out what that is. So we use the same properties, x squared, so using the Pythagorean theorem, adding the 10 squared equaling 17 squared. So x squared, add 100, 17 squared should be 289, if I'm doing my math in my head right. Yep. Subtract 100. So x squared will be 189. And if you take the square root of it, lucky, lucky, it's still 13.7 centimeters. Two ways, get the exact same answer. Alrighty, last example. Triangle ABC is inscribed in a circle. So basically it's inside a circle with a center of O. So this is O. I had to move the O over just to actually fit it in nicely. Angle AOB, so AOB is 100 degrees. So this angle right here is 100. Angle COB is 140. So COB is 140. We need to determine measures angle X, angle Y, and angle Z. So let's do a few things here. Well, the beautiful thing is we can find out angle X pretty nicely. Angle Z and angle Y would be a little more difficult to try and solve right now. The reason we can solve for X so nicely is because we have a circle right here. That is all one circle. And of course, by grade 9, you should know that there's 360 degrees in a circle. So we just subtract that 100, subtract the 140. Sorry, brain's not working this morning. Oh. I definitely typed in multiply. That's 120 degrees. So angle X is 120 degrees. Next one, we can solve for angle Y. Angle Y, because we have the arc AC, which has a central angle of X, and its inscribed angle. So we have this angle here, and we have this central angle right there. Well, we know that the central angle is going to be twice the size of the inscribed angle. So angle X is double the size of what angle Y would be. So if we just take the 120 and divide it by 2, angle Y would be 60. So the last thing is if we want to solve for angle Z, there's a few more things we can do. This is not the only way. This one's probably the fastest though. So if I just kind of get rid of those angles, and I'll get rid of that one, we know that angle X is 120 degrees. At the same time, if this is our center, any line drawn to the exterior of the circle will be the same, which means that's that radius. Well, we have now a triangle like this. We know that this one's 120, that side's the same, that side's the same. This is an isosceles triangle. And where did we have our isosceles triangle? I think it was right here. Yeah. Well, that means we have that central angle. The angles at the bottom are going to have to be the same. So in this question, this angle is going to have to be the same as that angle. Well, we could do some trial and error, but let's just do it by calculation. We know that there's 180 degrees in a triangle. So if we subtract the 120, you'd be left with 60. So we'd have to split 60 degrees evenly among those two spots. Well, to split evenly means to divide by 2. 60 divided by 2 is 30. And that's it. There you can have some fun.